Hey everyone, welcome back to the Math for Machine Learning series. Today, we're going to take a hands on programming approach to understand vector and matrices that are the building blocks of all machine learning algorithms. We'll see how to represent vectors in code and how this connects to concepts like span, basis, and linear transformations. Imagine we have three 2D vectors. Each vector has x and y component and we want to store them in a structured way. In Python, we can use a matrix where each column represents one vector and each row represents a dimension. For example, our first vector points 2 units along x-axis and 1 unit along y-axis. The second vector goes 4 unit along x-axis and 3 unit along y-axis. And the third vector points -3 along x-axis and 2 along y-axis. When we store them in a matrix, it's easy to see all the vectors together and perform operations on them efficiently. This representation is more than just numbers in a table. It's how computers understand and manipulate vectors. All data in machine learning, whether it's images, text, or sensor readings, can be represented as vectors. By structuring them into matrices, we can apply transformations, compute dot products, or even find eigenvectors, all of which are fundamental concepts in ML. Even before we start any computation, visualizing vector in this form helps us build an intuitive understanding of space, direction, and magnitude. Later, we can plot these vectors on a 2D plane, see how they relate to each other, and explore concepts like linear independence and span visually. This is the first step in connecting abstract math to practical ML implementations. Now that we have our 2D dataset stored as a matrix, let's visualize these vectors to better understand their direction and magnitude. First, we set the origin of all vectors at point 0, 0. This means every vector will start from the center of the plot. We then create a figure for plotting and use arrows to represent the vectors. Each arrow starts at the origin and points to the position defined by the vector's x and y components. Here, we're using different color for each vector, red, green, and blue, so that it's easy to distinguish them visually. To make the plot even more informative, we add labels next to each arrow. Each label corresponds to the vector index, helping us identify them on the graph. We also set the limit for x and y axis to ensure all vectors fit nicely in the frame. Adding horizontal and vertical lines at 0 helps provide a clear reference, while a light grid makes it easier to judge the vector's length and directions. Finally, we add a title and axis labels so that the plot is fully informative. And then when shown, this visualization shows us the position and orientation of all our 2D vectors, giving a clear picture of how they exist in the plane. Now, in the next part, we're going to implement some basic matrix operations in pure Python without relying on NumPy's built-in functions. This helps us understand exactly how these operations work under the hood. First, we define the function for matrix addition. This function takes two matrices of the same size and adds them element by element. Essentially, it goes through each row and each column, summing the corresponding entries and returns a new matrix containing these sums. Next, we implement the matrix transpose. Transforming a matrix flips its rows and columns. So, the first row becomes the first column, the second row becomes the second column, and so on. We do this by looping over the rows and columns and constructing a new matrix with the flipped structure. Then comes the dot product or matrix multiplication. This is a bit more involved. For each entry in the resulting matrix, we take the corresponding row from the first matrix and the column from the second matrix, multiply the element pairwise, and then sum them up. The function also checks that the number of columns in the first matrix matches the number of rows in the second matrix, because otherwise multiplication is not defined. To verify that our pure Python implementations are correct, we compare the result with NumPy's built-in function here. We create two example matrices, perform addition, transpose, and dot product both with our functions as well as with NumPy and print them side by side. When we look at the output, we can see that our manual implementation gives exactly the same results as NumPy. This not only confirms correctness but also strengthens our understanding of how these fundamental operations work, which is crucial when understanding or when working with matrices in machine learning. Now we'll explore how we can transform a 2D vector using scaling and rotation and visualize the effects. We start with a simple vector in 2 dimensions, pointing 3 units along x-axis and 2 units along y. This is our original vector, which we'll use as the basis for our transformation. Then we define a scaling transformation. Scaling changes the length of the vector along each axis. In example, we double the x component and reduce the y component by half. This produces a new vector that stretches more along x-axis and compresses along y. Now, we define a rotation transformation. Rotation changes the direction of the vector without changing its relative proportions. Here, we rotate the original vector by 45 degrees, which reorients it diagonally in the plane. We also combine transformation. For instance, we first scale the vector and then rotate it. The resulting vector shows both the stretching effect and the directional change, illustrating how transformations can be composed. To make these concepts fully clear, we plot all the vectors on the same 2D plane. The original vector is shown in blue, the scaled vector in green, the rotated vector in orange, and the scaled then rotated vector in red. Each vector starts from the origin, and we add labels next to the arrows so we can easily identify them. By looking at this plot, it becomes easy to see how scaling affects length, how rotation affects direction, and how combining transformation affects both. This visual approach helps us intuitively understand linear transformations, which are fundamental in many ML algorithms using PCA or feature scaling. Now in this part, we're going to explore linear independence of vectors in both 2D and 3D space and visualize the results. We start by generating some random vectors. For our 2D, we create 2 vectors, and for our 3D, we create 3 vectors. These vectors have higher integer values, which lets us see different scenarios each time we run the code. Next, we need to check whether these vectors are dependent or independent. In 2D, we can do this using the determinant. If the value of a 2 by 2 matrix formed by the 2 vectors is 0, then the vectors are dependent, meaning one can be expressed as a combination of others, otherwise they are independent. In higher dimensions like 3D, we use the matrix rank. We stack the vectors as a column in a matrix and calculate its rank. If the rank equals the number of vectors, they are independent, otherwise they are dependent. After checking the independence, we print the vectors along with whether they are independent or dependent. This gives us a quick numeric verification. Finally, we visualize the vectors. For 2D, each vector is drawn as an arrow starting from the origin. We use different colors to distinguish the vectors and add grid lines and axis labels for clarity. The blot dynamically indicates whether the vectors are independent or dependent. For 3D, we do something using a 3D plot. All vectors start from the origin, and various colors represent various vectors. The axes are labeled, and the plot shows whether the 3 vectors span the 3D space or not. This visual approach helps us intuitively understand the concept of span and independence, which are foundational in linear algebra and extremely important in ML tasks like feature selection, PCA, and understanding high dimensional data. Now in this part, we're going to explore the determinant of matrices and how they relate to orthogonal vectors with a hands-on demonstration in Python. We start by implementing manual determinant functions. For a 2 by 2 matrix, the value is calculated as the difference between the product of the diagonal elements and the product of the off-diagonal elements. For a 3 by 3 matrix, we use a slightly more complex formula that combines minors and cofactors. We test this function with example matrices, a 2 by 2 matrix and a 3 by 3 matrix. By computing the value of determinant manually, we get a numerical value that tells us important properties about the matrix. For instance, if the value is 0, the matrix is non-invertible, meaning its columns are linearly dependent. To verify our calculations, we compare the result with NumPy's built-in functions. This ensures that our manual implementation is correct and gives the same result as a trusted library. Next, we move to orthogonal vectors. Two vectors are orthogonal if their dot product is 0, meaning they are perpendicular to each other. In our example, we define a 2D vector and calculate the dot product, which confirms that they are indeed orthogonal. To visualize this, we plot the vectors on a 2D plane using arrows starting from the origin. One vector is shown in blue and the other one in red with labels for clarity. The plot include axes, grid lines and limits, so we can clearly see that the vectors form a right angle, illustrating the concept of orthogonality. So this exercise ties together two fundamental concepts in linear algebra: determinants, which helps us understand matrix properties, and linear dependence, and orthogonal vectors, which are crucial in understanding directions, projections, and many ML algorithms like PCA and feature decorrelation. Now, we'll explore one of the most important concepts in linear algebra and ML, eigenvectors and eigenvalues, and see how they relate to transformations. We start with a simple 2 by 2 matrix which represents a linear transformation in 2D space. This matrix can stretch, compress, or rotate vectors when applied to them. Next, we compute the eigenvalues and eigenvectors using NumPy's built-in function. Eigenvalues tells how much a vector will be scaled along a certain direction, and eigenvectors shows the direction that remain unchanged except for scaling when the transformation is applied. To illustrate this, we define two arbitrary vectors, one along the x-axis and one along the y-axis. These represent the standard basis vectors in 2D. When we apply our matrix to these vectors, we get the transform vectors, which show how the transformation affects any vector in the space. For visualization, we plot the original vectors in blue and the transform vectors in red. Then we plot the eigenvectors in green, scaling them for better visibility. This makes it easy to see the eigenvectors point in the special directions that are only stretched or compressed, while other vectors change direction as well. By comparing the original vectors, the transform vectors, and the eigenvectors on the same plot, we gain an intuitive understanding of why eigenvectors are so crucial in linear algebra and machine learning. This concept underpins many algorithms such as principal component analysis or PCA, which finds the direction of maximum variance in data. So that wraps up our programming demonstration on eigenvalues and eigenvectors. We've seen how to compute them, visualize their effects, and understand their significance in transformations and machine learning. So, if you found this video helpful, make sure to like, subscribe, and hit the bell icon so you don't miss the next video in our Math for Machine Learning series. Thanks for watching, and I will see you in the next one.